Broaching is a machining process that uses a toothed tool, called a broach, to remove material. There are two main types of broaching, linear and rotary. In linear broaching, which is the more common process, the broach is run linearly against a surface of the workpiece to effect the cut. Linear broaches are used in a broaching machine, which is also sometimes shortened to broach. In rotary broaching, the broach is rotated and pressed into the workpiece to cut an axis-symmetric shape. A rotary broach is used in a lathe-screw machine. In both processes, the cut is performed in one pass of the broach, which makes it very efficient. Broaching is used when precision machining is required, especially for odd shapes. Commonly machined surfaces include circular and non-circular holes, splines, keyways, and flat surfaces. Typical workpieces include small to medium-sized castings, forgings, screw machine parts, and stampings. Even though broaches can be expensive, broaching is usually favored over other processes when used for high-quantity production runs. Broaches are shaped similar to a saw, except the height of the teeth increases over the length of the tool. Moreover, the broach contains three distinct sections, one for roughing, another for semi-finishing, and the final one for finishing. Broaching is an unusual machining process because it has the feed built into the tool. The profile of the machined surface is always the inverse of the profile of the broach. The rise per tooth, also known as the step of feed per tooth, determines the amount of material removed and the size of the chip. The broach can be moved relative to the workpiece or vice versa. Because all of the features are built into the broach, no complex motion or skilled labor is required to use it. A broach is effectively a collection of single-point cutting tools arrayed in sequence, cutting one after the other. Its cut is analogous to multiple passes of a shaper process. The process depends on the type of broaching being performed. Surface broaching is very simple, as either the workpiece is moved against a stationary surface broach, or the workpiece is held stationary while the broach is moved against it. Internal broaching is more involved. The process begins by clamping the workpiece into a special holding fixture, called a work holder, which mounts in the broaching machine. The broaching machine elevator, which is the part of the machine that moves the broach above the work holder, then lowers the broach through the workpiece. Once through, the broaching machine's puller, essentially a hook, grabs the pilot of the broach. The elevator then releases the top of the pilot and the puller pulls the broach through the workpiece completely. The workpiece is then removed from the machine and the broach is raised back up to re-engage with the elevator. The broach usually only moves linearly, but sometimes it is also rotated to create a spiral spline or gun barrel rifling. Cutting fluids are used for three reasons: to cool the workpiece and broach, to lubricate cutting surfaces, to flush the chips from the teeth. Fortified petroleum cutting fluids are the most common. However, heavy-duty water-soluble cutting fluids are being used because of the superior cooling, cleanliness, and non-flammability. Usage. Broaching was originally developed for machining internal keyways. However, it was soon discovered that broaching is very useful for machining other surfaces and shapes for high-volume workpieces. Because each broach is specialized to cut just one shape, either the broach must be specially designed for the geometry of the workpiece or the workpiece must be designed around a standard broach geometry. A customized broach is usually only viable with high-volume workpieces because the broach can cost $15,000 to $30,000 to produce. Broaching speeds vary from 20 to 120 surface feet per minute. This results in a complete cycle time of 5 to 30 seconds. Most of the time is consumed by the return stroke, broach handling, and workpiece loading and unloading. The only limitations on broaching are that there are no obstructions over the length of the surface to be machined. The geometry to be cut does not have curves in multiple planes, and that the workpiece is strong enough to withstand the forces involved. Specifically for internal broaching, a hole must first exist in the workpiece so the broach can enter. Also, there are limits on the size of internal cuts. Common internal holes can range from 0.125 to 6 in diameter, but it is possible to achieve a range of 0.05 to 13 in. Surface broaches range is usually 0.075 to 10 in, although the feasible range is 0.02 to 20 in. Tolerances are usually plus or minus 0.002 in, but in precise applications a tolerance of plus or minus 0.0005 in can be held. Surface finishes are usually between 16 and 63 microinches, but can range from 8 to 125 mu in. There may be minimal burrs on the exit side of the cut. Broaching works best on softer materials, such as brass, bronze, copper alloys, aluminium, graphite, hard rubbers, wood, composites, and plastic. However, it still has a good machinability rating on mild steels and free machining steels. When broaching, the machinability rating is closely related to the hardness of the material. For steels, the ideal hardness range is between 16 and 24. Rockwell Ca hardness greater than HRC 35 will dull the broach quickly. Broaching is more difficult on harder materials, stainless steel and titanium, but is still possible. Broaching machines. Broaching machines are relatively simple, as they only have to move the broach in a linear motion at a predetermined speed and provide a means for handing the broach automatically. Most machines are hydraulic, but a few specialty machines are mechanically driven. The machines are distinguished by whether the motion is horizontal or vertical. The choice of machine is primarily dictated by the stroke required. Vertical broaching machines rarely have a stroke longer than 60 in. Vertical broaching machines can be designed for push broaching, pull-down broaching, pull-up broaching, or surface broaching. Push broaching machines are similar to an arbor press with a guided ram. Typical capacities are 5 to 50 tons. The 2-ram pull-down machine is the most common type of broaching machine. This style machine has the rams under the table. Pull-up machines have the ram above the table. They usually have more than one ram. Most surface broaching is done on a vertical machine. Horizontal broaching machines are designed for pull broaching, surface broaching, continuous broaching, and rotary broaching. Pull-style machines are basically vertical machines laid on the side with a longer stroke. Surface-style machines hold the broach stationary while the workpieces are clamped into fixtures that are mounted on a conveyor system. Continuous-style machines are similar to the surface-style machines except adapted for internal broaching. Horizontal machines used to be much more common than vertical machines. However, today they represent just 10% of all broaching machines purchased. Vertical machines are more popular because they take up less space. Broaching is often impossible without the specific broaching keyway machines unless you have a system that can be used in conjunction with a modern machining center-driven tooling lathe. These extra bits of equipment open up the possibility of producing keyways, splines and torques through one-hit machining. Rotary broaching, a somewhat different design of cutting tool that can achieve the irregular hole or outer profile of a broach, is called the rotary broach or wobble broach. One of the biggest advantages to this type of broaching is that it does not require a broaching machine, but instead is used on lathes, milling machines, screw machines or Swiss lathes. Rotary broaching requires two tooling components, a tool holder and a broach. The leading edge of the broach has a contour matching the desired final shape. The broach is mounted in a special tool holder that allows it to freely rotate. The tool holder is special because it holds the tool so that its axis of rotation is inclined slightly to the axis of rotation of the work. A typical value for this misalignment is 1 degree. This angle is what produces a rotating edge for the broach to cut the workpiece. Either the workpiece or the tool holder is rotated. If the tool holder is rotated, the misalignment causes the broach to appear as though it is wobbling, which is the origin of the term wobble broach. For internal broaching, the sides of the broach are drafted inward so it becomes thinner. For external broaching, the sides are drafted outward to make the pocket bigger. This draft keeps the broach from jamming. The draft must be larger than the angle of misalignment. If the workpiece rotates, the broach is pressed against it, is driven by it, and rotates synchronously with it. If the tool holder rotates, the broach is pressed against the workpiece, but is driven by the tool holder. Ideally, the tool advances at the same rate that it cuts. The ideal rate of cut is defined as rate of cut equals times sin. If it advances much faster, then the tool becomes choked. Conversely, if it advances much slower, then an interrupted or zigzag cut occurs. In practice, the rate of cut is slightly less than the ideal rate so that the load is released on the non-cutting edge of the tool. There is some spiraling of the tool as it cuts, so the form at the bottom of the workpiece may be rotated with respect to the form at the top of the whole profile. Spiraling may be undesirable because it binds the body of the tool and prevents it from cutting sharply. One solution to this is to reverse the rotation in mid-cut, causing the tool to spiral in the opposite direction. If reversing the machine is not practical, then interrupting the cut is another possible solution. In general, a rotary broach will not cut as accurately as a push-pull broach. However, the ability to use this type of cutting tool on common machine tools is highly advantageous. History. The concept of broaching can be traced back to the early 1850s, with the first applications used for cutting keyways in pulleys and gears. After World War I, broaching was used to rifle gun barrels. In the 1920s and 30s, the tolerances were tightened and the cost reduced thanks to advances in form grinding and broaching machines.